Okay, Year 12, welcome back. Next in the gripping instalment, we're going to look at some shape questions that I set yesterday. The first one says, explain how the electron pair repulsion theory, that's our VSEPR, can be used to deduce the shape and bond angle in PF3. So there are sort of stages that you want to go through when answering a question like this. The first is based on your periodic table. You want to look at the group that the element in question is in. And in this case, you're looking for the central atom, which will be the unique atom, which in this case is phosphorus. So I'd start by saying P has 5 electrons, 5 electrons in the outer shell. I'd then mention that it forms 3 covalent bonds with fluorine. And having done that, we have a total of 8 electrons in the outer shell. And then finally, just as you were shown in the videos that I linked to by the other chemistry teacher, you then need to mention how many of them are bonding and how many of them are non-bonding. So we have 3 bonding pairs and 1 non-bonding pair. Now if you sat there now thinking, okay, but how do I know how many covalent bonds it forms with fluorine? How do I know how many electrons that will have in its outer shell? And how do I know how many of those pairs are bonding and non-bonding? If you're stuck for that, you just draw a dot and cross diagram to help you. So we find phosphorus, we realise that it has 5 electrons in its outer shell. It needs to form 3 covalent bonds with fluorine, and conveniently, those 3 covalent bonds mean that we have our octet, and we can see that we have 3 bonding pairs of electrons shared between the phosphorus and the 3 fluorines, and 1 non-bonding pair. Once we've done that, we then need to move into using the VSEPR theory. So we found how many valence shell electron pairs there are, but we now need to talk about the fact that they repel. So we will then just say electrons or electron pairs repel as far as possible. Remember, they do that to maximise separation or in order to minimise the repulsion that they experience. The other fact that we know from VSEPR is that lone pairs of electrons or non-bonding pairs of electrons repel more than bonding pairs. But one of the classic mistakes in these questions is to dive straight in and tell the examiner about that fact, but fail to mention the basic overarching fact, which is that electron pairs repel as far as possible. Okay. But we can mention that lone or non-bonding pairs repel more than bonding pairs. But I would say that's a secondary thing because that has a small effect on the bond angle, whereas the fact that electron pairs repel one another has the biggest effect on the bond angle. So knowing that we've got 3 bonding pairs and 1 non-bonding pair, 4 pairs in total, and knowing our VSEPR theory in these 2 bullet points, we can deduce that this is going to be based on tetrahedral, but because we've only got 3 bonding pairs, we've only got 3 fluorines bonded to our phosphorus. The shape is based on tetrahedral, but it will actually be a trigonal pyramid. So shape, and I'm making it super clear to the examiner where I'm telling them the shape, because that was part of the question, deduce the shape of. So the shape is trigonal pyramidal, and I can put in brackets here, based on tetrahedral, because it's based on 4 areas of electron density, but this is the shape we get when only 3 of those are bonding. And the bond angle in this is 107 degrees. Now that answer is going to get you all 6 marks to this question. Notice I haven't written to the edge of every line, haven't filled every line, and I've got fairly big handwriting. There isn't masses to write in answer to shape questions, but it's important that everything you write is factually correct. Okay, if we were to have miscounted the number of electrons in the outer shell, or we were to have phosphorus forming some kind of bonds that it doesn't, we would very quickly find ourselves losing marks, particularly as it would lead us to the wrong conclusion about the shape and bond angle. This next question here is just a throwback because we are still building up to our end of topic test on atoms, atomic structure, electronic configuration, on time of flight mass spectrometry and so on. So just a reminder here, state the full electron configuration of a cobalt-2 ion. We find it on the periodic table, we see how many electrons it's got, and we start filling them in, and we remember to do superscript numbers to show the occupancy. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d7. It's a cobalt-2 ion, which means that it is in oxidation state 2 plus, or plus 2, sorry, but in this case it means that it is a CO2 plus ion. And so you'll notice that this is the electronic configuration of cobalt, but missing are the 4s electrons, because they're the first to leave as well as the first to go in when filling up. Okay, this is where my camera setup falls foul, but next question. The question is about elements in period 3 of the periodic table. State the element in the period 3 that will have the highest first ionisation energy. So which element is it, and why is it that one? So our highest ionisation energies always belong to our noble gases over on the right hand side of the periodic table in group 0. So it's going to be argon. And if we think about what the ionisation energy is, the amount of energy required to remove a mole of electrons from that mole of atoms in the gaseous state to produce a mole of 1 plus ions, what's going to affect that? It's going to be the nuclear charge and the amount of shielding on the distance from the nucleus. So why is argon the highest? Well, it has the largest number of protons of any element in that period, being on the right hand side, having built up largest number of protons. And we could there say the largest nuclear charge. That would mean the same thing in this case. And it has the same amount of shielding or the same number of shells as any of the other elements in that period. Okay. This next question here, I've actually removed on the version that I've sent you. So we'll move on. Chlorine's in a period 3 element. Chlorine forms molecules ClF3 and CCl2. Use your understanding of electron pair repulsion theory to draw the shape of ClF3 and the shape of CCl2. Include any lone pairs of electrons that influence that shape. So first of all, we've got ClF3. Now chlorine only needs to form one covalent bond to get an octet, to have a full outer shell of 8, but here we can see that it's forming 3 covalent bonds to 3 separate fluorines. So if I just very briefly do the dot and cross diagram for that, we're going to need 3 of our chlorine electrons to form covalent bonds to our 3 fluorines. And frustrating though it is, we need to make sure that this is accurate. So each of our fluorines needs to have its 7 dots representing its 7 outer shell electrons. So far I've drawn 3 of chlorine's outer shell electrons, but it's a halogen as well. It's in group 7, so it's got 7 electrons in its outer shell. So we also have 2 non-bonding pairs here. So in terms of areas of electron density, or bonding and non-bonding pairs combined, we've got 5. We've got 3 bonding, and we've got 2 non-bonding. And although there are a variety of shapes that you could conceive forming this way, we're actually going to end up with chlorine in the centre here, our fluorines here, here, and here, and our non-bonding pairs coming towards us and going away from us in our diagram. Now the bond angles here are, in this T-shaped molecule, are 90 degrees on the right angle between the fluorine sticking up and down and the fluorine out to the side, and 120 degrees between all of these in this plane here, except for the fact that these have a slight extra repulsive effect. So we might end up going to maybe 121 degrees here and 89 degrees between these, but that'll do based on that 120 degrees there. There are no angled marks available here, so we're not fussed about that. In terms of our carbon dichloride here, now this is a particularly unusual molecule, but if we just work with what we've got, we know that carbon is forming two covalent bonds, so it's forming one to chlorine here. Now it can't form a double bond to that chlorine, as it would do in something like carbon dioxide, because this chlorine is only willing to share one electron, only needing one electron to fill its outer shell. So we end up with this as bonding electrons. We've drawn two of the outer shell electrons of carbon so far, so the remaining two electrons are up here as a lone pair. So this time we have three areas of electron density, two bonding pairs and one non-bonding pair. And when that's the case, we end up with a shape that is bent. So we've got Cl, C, Cl here. Again, no marks for the bond angle, but we do need to include the lone pair of electrons on the carbon there. So it's another example of where drawing the dot and cross diagrams will help give you an idea of the number of bonding and non-bonding electrons. So remember it here, it was two bonding and one non-bonding. And the difficult part, and the bit that some of you have rightly said to me is hard, the difficult bit is remembering what shape these different combinations of bonding and non-bonding pairs of electrons form. And that is difficult, but with a bit of flashcard work, for example, we will get there. It wants the shape of this one over here, which we've just said is bent. Okay. The last question that I've sent you, question 3 down here, says a molecule of ClF3 reacts with a molecule of AsF5 as shown in the following equation. Use your understanding of electron pair repulsion theory to draw the shape of the AsF5 molecule and the shape of the ClF2 plus ion. So that's a single positive charge on a ClF2. We have just drawn a ClF3. We're looking here for a ClF2 ion that forms when it loses one of those fluorines. It wants you to include any lone pairs of electrons and name the shape made by the atoms in AsF3 and in the ClF2 plus ion, and predict the bond angle in the ClF2 ion. I think the easier of these two is the AsF5. We've got As in group 5, similar to the phosphorus that we started with today. So we're going to have our As in the centre, and we've got a trigonal bipyramid shape here. So we've got F going up and down, forming the tip and the base of the two pyramids, and then in the centre we've got one F in the plane of the paper, we've got one coming towards us, we've got one going away from us. So we've got our 5 bonding pairs of electrons separated out to give us our trigonal bipyramidal shape. Okay, so our trigonal bipyramidal shape. For our ClF2, we've got a positive charge here, which means that we've lost one of our electrons. So a quick dot and cross diagram to explain what's going on here. We've got a covalent bond to one of our Fs, covalent bond to our other F here. We mustn't forget all of the outer shell electrons. If we ever draw a dot and cross diagram, it needs to be accurate. So the outer shell electrons of all of the atoms involved. Okay, so we've got our 7 electrons around each of our F. We've drawn 2 of our chlorine electrons so far, and of course it would be a total of 7 if it were chlorine normally. But this is a positively charged ion, and you'll remember from GCSE and from the work we've done so far that a positively charged ion is positive because it has lost an electron. So instead of drawing the remaining 5 electrons that chlorine would have to make up to 7 crosses, we're only going to draw 4 because it's lost one of those electrons. And when we do that and count up our bonding and non-bonding pairs, we've got 2 bonding and 2 non-bonding pairs. Okay? And this is actually analogous then to water. 2 bonding and 2 non-bonding pairs is the structure we have between oxygen and hydrogen in water. So when we draw it, we have Cl here, we have F and F, both in the plane of the paper, and then sticking up above, coming towards us and going away from us, we have our two lone pairs here. This shape then, just as it was for water, is our bent shape. And if we had to predict a bond angle for this, well, if it were tetrahedral, which bent is based on because it's got 4 areas of electron density, we'd expect the bond angle to be 109.5. A single lone pair would bring that down to 107, but with two non-bonding pairs, this bond angle here gets reduced further to 104.5 degrees. Okay, so some different styles of shape questions there. All of them rely on you knowing the relationship between the number of bonding and non-bonding pairs and what that looks like in terms of shape. And most of them will require you to be able to draw a dot and cross diagram to first figure out how many bonding and non-bonding pairs of electrons you've got. And if you're not sure how to do that, 2 previous videos will run through both of those skills. Okay, well done for doing this work from home. It's not easy, I know. Most important thing, once you've had a go at these questions and been through and marked, the most important thing is to keep up your revision for that first end of topic test, which will be coming up after half term. Okay, well done. Thanks for your time.